All right, now that we have looked at how to solve some various quadratic equations, let's take a look at what's called the discriminant. Now, just to refresh your memory, if I give you the quadratic formula, okay, the quadratic formula comes from solving the quadratic equation. So recall the quadratic formula finds, that would be better, solves the quadratic equation. So if I give you the quadratic equation, ax squared plus bx plus c equals 0, we know by the fundamental theorem of algebra that we're going to get two solutions. We've learned how to factor to find them, complete the square to find them, the quadratic formula to find them. The quadratic formula always works. Completing the square always works. So if we complete the square on this, which we did last section, we will find that the solutions become the opposite of b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay, that's the quadratic formula. Now we know that. We've worked with it. Now we're going to take a look at what's called the discriminant. And in my opinion, it's basically logic. If I use the vocab, the discriminant refers to the radicand. Okay? The discriminant refers to the radicand. Well, we've talked about this before. The radicand is whatever's under the square root. So the discriminant is this expression. Okay? Let me get a better color. That one. So, okay, the discriminant ends up being whatever is underneath that radical sign. So in this case, the discriminant is just the b squared minus 4ac. It does not include the square root. It's just the radicand. Now, I'm basically done because we've already talked about square roots. We've already talked about imaginary roots. We've talked about complex roots. Okay? So let's just logically think about this. We only have three choices for what could be underneath this square root. We could have a number which is positive. We could have a number which is negative. We could have a number which is 0, since 0 is neither positive nor negative. So let's look at and logically figure out what happens in each of those situations. All right. So if the discriminant, b squared minus 4ac, is positive, let's think about it. Can we take the square root of a positive number? Can we take the square root of 1, square root of 2, square root of 4, square root of 12, square root of 16? Well, yes, we can take the square root of a positive number. We either get a rational number, or we end up with an irrational number, something that's a decimal that goes forever and ever and ever and ever and ever. So yes, we get an answer. In fact, we're going to get two answers because it says take the positive and the negative root. So if the discriminant is positive, then there are two rational, now let's do it this way. There are two real roots. I think I'm going to move this over a little bit. That way I can leave it here and I can use examples. So I'm just going to move this over so I have a little more room. I'm going to write the same thing. If the discriminant b squared minus 4ac is positive, then there are two real roots. They might be rational, they might be irrational. But they are real because we're allowed to take the square root of a positive. If the discriminant equals 0, then, again, you could memorize, but why? Why? Just analyze. If 0 is in here, what's the square root of 0? 0. So then it would say the opposite of b plus 0 over 2a, opposite of b minus 0 over 2a. Well, if I add and subtract 0, all I end up with is the opposite of b over 2a. I'll kind of say that again. If this discriminant 0, the square root of 0 is 0, so that part's gone. And so all we're left with is the opposite of b over 2a. Now, knowing we have to have two answers, then we end up with a double root. So there are two double roots. Okay. It's probably better to say there is one real double root. That's a better way to say it. I apologize. Because you're going to get the same answer twice. One real double root. I'll do an example and show you what I mean by this. And then when we start to graph, it will become more obvious. Well, then our only other choice for the discriminant is if it is negative. So if the discriminant is less than 0 and it's negative, well, again, we have devoted half a chapter to that. Can we take the square root of a negative number? Can we take a square root of a negative? Well, the answer is yes. Our answer is not going to be real, it's going to be imaginary. But we can do it now. Then there are, and again, let's think about this for a minute. If this is a negative answer, I'm going to end up with a term plus or minus another term. So those are conjugates. Those are conjugates when you're adding and subtracting the same terms. So what we end up with is we end up with two conjugate complex roots. Okay, so let's practice. Let's practice. All right, let's say, for example, I just ask you to determine the nature of the roots. We've talked about it in the past. I want to refresh your memory. Whenever you see that word root, it's a synonym. Roots are also called solutions. Roots are also called zeros. Okay, looks like that's off the screen a little bit. So I could have said find the solutions, the nature of the solutions. But instead, we say find the nature of the roots. Find the zeros. When we go to graph, those will become x-intercepts. So these are all synonyms. Roots mean solutions, which mean x-intercepts, which means zeros. Okay, so right now we're talking about them in terms of roots. Determine the nature of the roots. So in other words, are they real roots or are they complex roots? So here's a first couple examples, okay? Let's say I give you the following. X squared minus 4x plus 13 equals 0. X squared minus 4x plus 13 equals 0. Now we can solve it by completing the square or the quadratic formula. I want to just figure out the nature of the roots. So the nature of the roots, again, what we mean by that, the nature of the roots, we want to know, are they real roots or are they complex roots, and how many of them do we have? So I'm going to use the discriminant. Well, I know our A value is 1, our B value is negative 4, and our C value is positive 13. So if I figure out B squared minus 4AC, if I just figure out the discriminant, call that capital D to represent discriminant, B squared, negative 4 squared minus 4 times 1 times 13. That gives us 16 minus 52. I don't even need to know what the actual answer is, because I can already tell whether or not it's positive, 0, or negative. But in this case, if you need to because you want to be complete, this is negative 36, which is less than 0. So what do I know about the solutions? I know there will be, if it's less than 0, that's negative. So I'm going to get 2 conjugate complex roots. And of course, I could then find them by using quadratic formula or completing the square. Okay, so at this point, let's do another one. Let's determine the nature of the roots. And let's say I give you this one, x squared plus 7/3 of an x plus 2/3 equals 0. Now it's a quadratic equation. It's an equation. If you'd like, you can let a equal 1, b equal 7/3, c equal 2/3. But if it's an equation, you could eliminate the fractions and then examine the problem. Might make it a little easier. I'm going to choose to eliminate the denominators by multiplying everything by 3. So if I choose to multiply everything by 3, I get a 3x squared. The 3's reduce, so I get a 7x. The 3's reduce, so I get a 2. And 0 times 3 would be 0. That's what you get if you multiply by that common denominator being 3. Well, now this might be a little bit easier to solve. Okay, some of you may go, oh, I can solve it by factoring. You can probably even mentally start seeing what the factors are. But let's go through this. So what do I know? I know the A value is 3. I know the B value is 7. I know the C value is 2. And I know I can figure out the nature of the roots if I use the discriminant. So the discriminant is b squared minus 4ac, 7 squared, 4 times 3 times 2, 7 squared, minus 12 times 2 is 24. And once again, once you notice that it's positive, negative, or 0, you don't technically need to finish, but if you want to, we end up with 25, which is clearly greater than 0. So if the discriminant is greater than 0, we know that whatever's under the square root's positive, I'm allowed to have that, so I end up with a plus or minus 2 real roots. So we know there will be two distinct, you know what, I think I'll put that in there. They're going to be independent. They're going to be unique, real roots. And of course, I could have factored this one to solve it. I could have completed the square, could have used the formula. So I've given you an example of two complex roots, two real roots. Let's come up with what it looks like when it is a double root, okay? So let me give you one that looks a little intimidating at first glance, but it's not. It's not. So here, let's get a little more creative. Let's sort of blend what we've done recently to sort of spiral back around. So I'm going to give you this one right here. I'm going to give you 5x squared plus 2 root 10x equals -2. Okay, in order to solve this, I can complete the square, use the quadratic formula. In order to figure out the nature of the roots, I only need the discriminant part, the radicand, the part under the radical. So I'm going to first bring the 2 to the left-hand side so that I can identify the parts and pieces. I can see our A value is 5, our B value is 2 root 10, and our C value is +2. So let's check out the discriminant. The discriminant is the B squared minus 4AC. So the discriminant is 2 root 10 squared minus 4 times 5 times 2. Well, we've done this. This was last chapter. If I square 2 root 10, I get 4 times 10. This gives me 20 times 2 is 40. So the discriminant ends up being 0, which logic tells me if I have a 0 in here, then I'm taking the opposite of B plus or minus nothing. Well, that's just the same as not having anything there. So the opposite of B over 2A is my only answer. So this implies, since the discriminant is 0, we now know there will only be one real root, so it must show up twice. Must be a double root. All right. So let's try a couple of them so that we can determine the roots and then we can perhaps solve it. All right. So let's say I'm going to try to pick some out of your homework. I'm going to choose number 16. And that's it, you guys. I mean, that's the main idea. Let's practice some. So we are going to solve. And I also want to determine the nature of the roots. So we just talked about that. If we're talking about the nature of the roots, again, all of this means, are they real or are they imaginary? Are they complex? That's all that means, because that's going to help us when we go to graph. All right, so here is number 16 in your book. 4y squared plus 12y plus 9. Now, first of all, it just says solve. We've now done factoring. We've now done completing the square. We've now done quadratic formula. So if the directions don't tell you a specific way, you can use any technique you'd like. It does not matter. Okay? Solve by, and you choose. Unless I tell you, you can use any method you want. You just have to show me your work so I know what you've done. Some of you always like factoring. Some of you have now found completing the square is wonderful because it always works. Some of you prefer quadratic formula because it always works. There's a lot of chances for error, but it always works. I'm just going to start at the top, and if it doesn't work, then I'm going to choose one of the other ones. So if I want to check about factoring, and if I remind myself 4 times 9 is 36, what are factors of 36 that add up to 12? Well, actually, I have 6 and 6. So I'm guaranteed it's going to factor, so I'm going to go ahead and factor. Just to refresh your memory, that means I'm going to rewrite the 12y using those two coefficients, the 6 and the 6, and then we're going to factor by grouping. Now, I also showed a lot of you the method I use, which involves kind of foiling, but when in doubt, go back to what we know. Factor a 2y out. You all know how to factor. Factor a 3 out, and I should end up with the exact same group. And sure enough, I do. Use the distributive property to factor out the 2y plus 3, and notice I'm left with 2y plus 3. So I have a double root. They're both identical factors, so I have a double root. So in either case, when I set 2y plus 3 equal to 0, I get negative 3 halves twice. I get negative 3 halves twice. Notice this is a double real root because it showed up twice. So back in chapter 4, the answer in the back would have said dr, double root. Okay? Again, when we go to graph this, you're going to see what that means. Now, determine the nature of the roots. Let's make sure this is done correctly. Probably should have done it first, but it doesn't really matter. Let's check the discriminant just to see if we got the right scenario for our answers. Let's check the b squared minus 4ac. A is 4, b is 12, c is 9. b squared minus 4 times our a value times our c value. 144 minus 16 times 9. Notice we get 144 minus itself, so I get 0. If the discriminant's 0, then sure enough, if I had used quadratic formula, I would have had the same answer twice. I would have had negative 12 plus 0 over 8, and I would have had negative 12 minus 0 over 8. So I would have had the same answer twice. Okay. That's pretty much it. The only thing we can do is make the problem start off looking a little different. So you're going to be allowed any method. You can solve using any method. Oh, let me give you one of the, here we go. Same concept. Let's elevate the conceptual idea. Let's elevate the concept of this. This is number 32. We are given 3x squared minus 6x minus k. 3x squared minus 6x minus k equals 0. And we want to figure out the values of k that would make it give us 2 real answers, 1 real double root, or 2 complex conjugate roots. So we have 3 different parts. Okay? Find k. How did they word it? Find the values for k for which each equation has the following. For which the equation has, part A real double root. Part B, 2 different real roots. 2 different or unique real roots. And you can probably guess the third one, complex or imaginary roots. Now I know some of you, as soon as I wrote down the k, you kind of sighed and grunted and went, ugh, not one of those k problems again. This is a brilliant question for asking about concept instead of mechanics. So let's look at what it takes to be a real double root. In order to get a real double root means the discriminant must be 0. Okay, so in this case, I know that the discriminant must equal 0. All right, well, you are months older than you were the last time we did a problem involving k. Just follow the directions. A is 3, B is -6, C is -k. Just follow the directions. Life is simple. Follow the directions. Opposite of b squared minus 4 times a times c equals 0. -6 squared. -4 times -k is a positive. This would be a 12. K equals 0. Move the 36 to the other side. So 12k equals -36. Divide by 12. Notice what we end up with. In order for this to work, k must be -3. So if I'm writing a test or quiz and I want a real double root, all I have to do is work backwards and make this equation 3x squared minus 6x minus -3. So plus 3 equals 0. I'm guaranteed 2 identical factors. I'm guaranteed 2 identical answers. So let's do it again. If we want 2 different real roots, maybe I should put unique right here. Unique or different. Then I know the discriminant has to be positive. Okay. B squared minus 4ac needs to be positive. Well, Well, don't we already know what the discriminant is? When we substituted it in, I'll do it again. B is -6, A is 3, C is -k. That's got to be greater than 0. 36 plus 12k. See, we already figured out the discriminant up here. 36 plus 12k. It's got to be greater than 0. Subtract the 36. Divide by 12. I have to simply choose a number that's larger than -3. It could be -2, -1, 0, 1/2, 0.7, whatever you want, larger than -3. If I substitute in, I'm guaranteed 2 different real answers. They might have a square root in them, but that's okay. They could be irrational. And then I think you have the idea. If we want imaginary roots, then we need to make sure our discriminant's less than 0. So in this case, we know that b squared minus 4ac had better be negative. And we already figured out the b squared minus 4ac. So I'm just going to kind of fast forward. That means our 36 plus 12k that we found this to be has to be negative. Move the 36 over. Divide by 12. And in order to guarantee imaginary conjugate pairs, those complex conjugate pairs, I'd have to pick -3. Okay. So I think we're in pretty good shape because we've done problems in the last 2 sections that involve fractions, like number 28, 29, 30. We've done problems in the last couple sections, like 25 and 26, where you need to expand it and combine like terms. We've done problems with radicals. So I think I'm comfortable stopping there and having you practice the discriminant and then use any method, factoring, completing the square, or the quadratic formula to solve it if they ask for it. All right, so there you go. Have a great rest of your day, and we will talk a little bit later.